Hi guys, welcome back to the channel. In today's lecture, we are going to discuss one problem on influence line diagram in which we'll find the maximum moment at a particular point. Okay, so we'll come directly to the problem. So problem is that we are given a simply supported beam, and at point P, we need to calculate what will be the maximum moment generated at point P when this load system is traversing from left to right. This is the movement of the load, and one more condition is given that either end can be leading. Okay, so another condition is either end can be leading. So if this is the condition, this is our one system of loads. Okay, so the second system will include in second system the loads will act like this. Okay, here 120 kilonewton load at this point, and here 110 kilonewton load at this point. Okay, so this is the two load system for which we need to find the maximum bending moment at point P. Okay, either end can be leading. Okay, so that's why we have two system of loads, right, in which this is what you know is this is tail, and this is basically the head of the load, and here it is, this is the tail, and this is the head of the load, right? So in this problem you can see that this is a there is a UDL also, and there is point load, there are point load also. So we need to analyze this problem. Okay, so first what we will do over here, first step is that we need to draw the ILD when unit load is traversing this beam. Okay, when unit load is traversing this beam, the maximum moment will generate at generate at point P. Okay, when the unit load is traversing along AB, the maximum moment will generate at point P. Okay, so when the unit load will act at point P, it will have the maximum ordinate. This thing we have already discussed. Okay, and the ordinate of this will be nothing but 2 into 8 divided by total length. Okay, so it will be 1.6, right? So this is the ILD due to unit load. This is due to unit load. Okay, unit load, and ILD is of moment, MP moment. Let us suppose this point is MP. Okay, now by using this we will see which positioning of these two load system will give us the maximum moment, okay, at point P. So at first I'm considering, let us suppose I'm considering this load system, okay, where this 10 kilonewton load is at the head, and the end of this UDL is at the tail. Okay, but the point here to be noted is that the length of the UDL is greater than 10 meter. That means that the length of the UDL is greater than the span of the beam. Okay, that is the important thing over here, right? And one more thing we have discussed in the past lectures is that to calculate the maximum moment at point P, average load at AP should be equal to average load at PB. This thing should be very, very clear. Okay, average load, this thing we have already discussed. Average load on AP must be equal to average load on PB. Okay, so by taking this condition, we will see at what positioning of the load this condition will be satisfied. Okay, so now consider, let us suppose now we'll consider this beam. Okay, and this is the point P, right? So first what I am doing over here, and we already know that the maximum moment will generate in case of the point load, the maximum moment will generate under the point load. Okay, so this load is combination of two loads. This is the UDL, and there are 2 points load. Okay, so what we will do over here, let us do one thing. Okay, first I'm applying the point load at this point, 20 kilonewton load at this position. Okay, and 10 kilonewton load will be at this location, this 2-meter distance. Okay, and this length of the beam is greater than 10 meters. So this portion can this portion, there will be the whole UDL at this portion. Okay, this portion will be at this portion, there will be complete UDL. Okay, because the L is greater than 10 meter. Okay, so this portion, at this portion, whole length will be under uniformly distributed load. Okay, the uniformly distributed length will act on the whole length AP, right? So, and this distance is 2 meter and this distance is 8 meter, right? So if we calculate what will be the average load of what will be the average load at different spans, okay, at AP and PB. Okay, so this is the uniformly distributed load. Okay, so on AP I can write the average load on AP. Average load will be equals to 10 kilonewton per meter. Okay, so this is the UDL. Average load per unit length is nothing but UDL only. So this is 10 kilonewton per meter. Okay, and one more thing I am doing over here is that I am taking this P load, this at the load at this point P. I am assuming that whole load 20 kilonewton is transferring on this PB, or you can say that this 20 kilonewton load is acting just at the left of P, just at the right of P. Assuming this 20 kilonewton load is acting just at the right of P. Okay, so when this condition happens, so average load will be nothing but 20 plus 10 kilonewton divided by 8 meter, and this value comes out to be 30 divided by 8. So you can see that from this combination of load, you can see that the average load on this position, average load on this portion, and average load on this this portion are not equal. So this is so for this load combination we won't get a maximum moment at point P. But you are seeing, at the point P, the 20 kilonewton load is acting, but we are not getting the what you can say that we are not getting the maximum moment. Why? Because there is some UDL also. Okay, that will also control the maximum moment at this point, right? And average load is also not coming same for both the spans, which is AP and PB. So we need to alter the loads conditions. What we will do over here, you can see that, as you can see that this load during when this condition when for this condition the AP average load on AP average load is greater than average load of PB. Okay, so I need to transfer some of the load at this for this portion also. So what that means is that some portion of the UDL will come again on this portion, this PB portion, right? So now let us check for that condition. Now our condition will look like this. If this is the simply supported beam and this is the point P. Okay, so I'm assuming that some of the UDL is transferred to this point PB. Okay, let us denote the length will be X. Okay, and here 120 kilonewton load is acting, 20, and at a distance of 2 meter again 10 kilonewton load is acting. So this is again 2 meter and this is at 10 kilonewton, and you can see that the whole this portion AP will be covered by the whole length will be covered by UDL. Okay, why? Because the L is greater than 10 meter. Okay, L is greater than 10 meters. So this distance is 2 meter. This distance is 2 plus X only. So it will be definitely be smaller than 10. So this portion will be the whole portion will be occupied by the UDL. Okay, the uniformly distributed load will act on this complete portion. Okay, so now we will calculate what will be the maximum moment that will be generated at this what will be the average load for these two spans. Okay, so if I calculate the average load for AP again the average load will be 10 kilonewton meter. Okay, and if I want to calculate what will be the average load for PB it will be nothing but 10 into X plus 20 plus 10 divided upon 8. This is the average kilonewton, average load on span PB. On span PB. Now for maximum moment, you can say that this 10 kilonewton load per meter should be equals to this equation 10x plus 30 over 8. Okay, for the maximum amount of, if we want to have maximum moment at this point P, this condition should satisfy that average load on AP should be equal to average load on PB, right? So again, if we solve this equation, so we'll get value AT equals to 10x plus 30, right? So if from here x equals to 5 meter. Okay, so this is a very important value we are getting from x equal to 5 meter, which means that this distance x is 5 meter. Okay, so the length of the UDL for PB portion, which is acting on PB, is of 5 meter, right? And this distance is again 1 meter. Okay, so the length of UDL which is coming on PB portion is 5 meter, and plus 2 point loads are also coming. Okay, now what we will do, we will calculate what will be the ordinate for this load system. Okay, for that what we need to do is, this is our ILD due to unit load. Now we will calculate what will be the ordinates at these point loads, right? So when this is the distance 8 meter, okay, and at a distance of 5, so this distance will be 3. Okay, and again we need to calculate one more ordinate at under the 10 kilonewton load, and the distance is from here, it is 1 meter. Okay, now you can see that this ordinate, we already know that this value is 1.6. Okay, this ordinate value is 1.6. So if we use the concept of similar triangles, I can say that 1.6 over 8 is equals to, let us suppose this is y dash, y1 dash over 3. I can write like this. So the value comes out to be 0.6. Okay, so this y dash value is nothing but this ordinate value is 0.6. Okay, and again if I calculate the ordinate value at this point at a distance of 1 meter, then the value will be 0.6 divided by 8 equals to x y2 dash over 1. So the value comes out to be 0.2. So the ordinate value at this location is 0.2. Okay, so this thing we have calculated. Now we'll calculate what will be the value of the moment coming for this system. Okay, so the point P, so the point at the point under the 20 kilonewton load, the ordinate will be 0.6. Okay, so what we will do for the unit load, the ordinate will be 0.6. Okay, if the point load is acting, 20 kilonewton load is acting at that point, then the ordinate will be 20 into 0.06. Okay, 20 into 0.6 plus 10 into 0.2 plus. Now the important thing comes about the UDL. Okay, so let us assume that at a distance of x, I'm assuming a dx element over here. Okay, so the load of point load due to this dx element, due to this dx element will be intensity of UDL into length of that element, that is W into dx. Okay, and the ordinate, let us suppose this ordinate is nothing but y dash. Okay, let us suppose this ordinate is y dash. So the moment dm due to this element at point P will be nothing but this W into dx, which is total point load, into this ordinate. y dash, right? And if I integrate this thing, so then it will become mp, okay, and this w will come outside, and this value will be dx, integration of dx into y, or you can say that this is y dot dx, and which will be nothing but this is basically the area under this graph, okay, this area which is coming under this UDL, right? So the area which is coming under the UDL is nothing but this area, okay. So this y dot dx is nothing but area under UDL, okay. So what we will do over here, we will simply multiply the intensity of the UDL plus the area of this up to this portion where the UDL is acting, okay. Now we need to calculate the area of this triangle plus this trapezium. Okay, so what will be the area? So area is nothing but this distance is 2 meter. So I can write the intensity of the UDL is nothing but 10 into area of first 1 into 2 into 1.6. Okay, this is a triangle. So half into base into height into half into base into height, plus what will be the area of this trapezoid? Trapezoid area will be half into sum of parallel sides, yani 1.6 plus 0.6 into this distance. This is nothing but into 5. Okay, this distance is 5 meter. Okay, so if we calculate this value, so if we solve this complete value, this complete expression, the value comes out to be 85 kilonewton meter. Okay. For this combination of load, we can say that the maximum moment generated at the point P will be equals to 85 kilonewton per meter. Okay. So this is the thing now. So for this load system, the maximum value of the moment generated will be 85 kilonewton per meter. Okay. Now we'll see, is there any load system? Is there any other load system for which the average load on AP span will be equals to PB span? We need to check for that also. Okay. So again, we'll draw one beam over here. This is the point P. So the UD in ILD due to unit load, ILD for the moment when the unit load is traversing this beam, and this is 1.6. Okay. Now let us consider some other load system. Okay, there will be some other load system will look like this. Let us suppose this 10 kilonewton load is not coming on the beam. Okay, this 10 kilonewton load crosses the beam. Let us suppose this 10 kilonewton load at this point and 20 kilonewton load is acting on this portion. So the UDL will look like this. Okay. Now if we calculate the average load on AP will be nothing but it will be 10 kilonewton per meter, because only the UDL is acting at that point, and average load on PB will be equals to 10 into x plus 20 divide over my this distance is nothing but 8 meter. Okay. So for the maximum, this thing should be this 10 kilonewton should be equals 10 kilonewton per meter load should be equals to this value for if we want to have maximum load, maximum moment at P. So it will be x equals to 6 meter. So from here we can see that this UDL distance x is equals to 6 meter. Okay, and this distance is 20. So this remaining distance will be 2 meter. Okay, and this 10 kilonewton load is acting, you can say that acting at the support only. Okay, so if that load is acting on the support, you cannot say that this load is transferred to the beam, or this load will be taken care, this load, whole load is transferred to this support only. Okay, you can understand like this, or you can say that this load had just crossed this support. Okay, that is also, you can say from here that this load is about to cross this support. Okay, this about to cross this beam, so no load is transferred on this beam, right? So now at a distance, now the ordinate at a distance of 6 we need to calculate, because 20 kilonewton load is acting at this point only, and at 10 kilonewton is at, the ordinate is at 0, so we need not to worry about it. Okay, so now if we use the similar triangle concept again, 1.6 over may 8 equals to x, this y dash upon may, this value is 2. Okay, so 2, so that is equals to y dash is nothing but 0.4. Okay, so this ordinate comes out to be 0.4. Okay, so if this ordinate comes out to be 0.4, then you can say that this 20, the value of the maximum moment MP will be 20 into 0.4, okay, plus 10 into 0, and plus we need to calculate again the area which comes under the UDL. Okay, so this is the area, so again plus sign, again the intensity of UDL is 10, and the area will be half into 1.6 into 2 plus half into sum of parallel sides is 1.6 plus 0.4, and into may 6 meter, right? So if we calculate this value, so the value comes out to be 84 kilonewton. Okay, 84 kilonewton per meter. So this is another case for which the value comes out to be 84 kilonewton meter. Okay, but we already got the value, maximum value 85 kilonewton meter for the previous case which we have discussed. Okay, so this case is more critical than this case, right? So now let us now again we'll check, is there any other load system for which this average load is equal? Now you can see that if this is the beam and this is the point P, okay, length of this UDL is greater than 10 meter. So there may be the chances, then there are the chances that this load, this 20 kilonewton load and 10 kilonewton load is not coming on the beam, and the whole beam is covered by this UDL. Okay, so and the intensity of this UDL is 10 kilonewton per meter. Okay, now you can see that average load on AP will be 10 kilonewton per meter, and average load on PB will be equals to 10 kilonewton per meter. Okay, this is 2 and this is 8 meter. Okay, and the ILD for unit load, ILD for the moment when the unit load is crossing, it will look like this, right? So again you can see that the average load on AP is equals to average load on PP, because the whole beam is covered by the UDL only. Okay, so the average load on this portion is 10 kilonewton per meter, and average load on this portion is 10 kilometer, because there is no point load acting on the beam. Okay, so now what we will do, we need this ordinate, we already know this value is 1.6. okay, so the UDL is acting on the whole beam, so we need to find this area to calculate MP. So MP will be nothing but half into 10 intensity of the load plus area is 1.6 into, and this length is again 10 meter. So this is area multiplied by the intensity of the load. Okay, this is the area and this is multiplied by the intensity of the load. Okay, so if we calculate this value, this comes out to be 0.5 into 10 into 1.6 into 10. So this value comes out to be 80 kilonewton per meter, 80 kilonewton meter. Okay, so this is our least critical case. Okay, so first previously is 85, then 84, then this is 80 kilonewton meter. Okay, so this is the way you solve the problem like where we have the point loads and the UDL are acting for the same in the same beam where we have the both UDL and point loads. Okay, so this is the way you solve this problem. Okay, by taking the concept of that average load on the left side of the point should be equal to the average load on the right side of the point. Okay, so we have discussed one system. Now we will discuss another system when this portion is leading, this UDL is leading, and these two portion and this 10 kilonewton is coming at the tail. Okay, so now let us draw the beam again over here. Okay, and we need to find the load at point P, right? So here also you can say that here also we are saying that the average load concept we need to use over here, and let us see how do we use it. Okay, so let us suppose I am assuming that this 20 kilonewton load is acting at point P. Okay, and this 10 kilonewton load is acting at this support. This is 2 meter only, and this is 20 kilonewton meter. Okay, and this is covered by UDL because this length is greater than 10 meter, but this length and this length is 8 meter. So this whole portion will be covered by UDL. Okay. Now we are assuming, now let us assume that this 20 kilonewton load is acting, this 20 kilonewton load is acting just at left of P. Okay, just at left of P. Okay, so the average load on AP, so average load on AP will be nothing but 20 divided by what? 2, and the value comes out to be 10 kilonewton per meter, right? And the load which is coming on this PB will be equals to the load which is coming on PB will be equals to is nothing but it will be also be equals to 10 kilonewton per meter, because no load is transferring to no portion, there is not a portion of 20 kilonewton load which is transferring on the beam, because I have assumed that it is just at the left of P. Okay, so there is no portion, so the portion of the load of 20 kilonewton on this PB is negligible. Okay, so average load on this portion is also acting 10 kilonewton per meter. So you can say that this condition is satisfying, that average load on AP will be equals to average load on PB. So if this is acting on left side, so this load will move just left of support. Okay, this will leave the beam, right? So if we need if I need to calculate this thing, if I calculate this thing, the maximum moment due in for this load condition, let us do that in this thing. Okay, so now you can see that okay, so first we draw the ILD due to unit load. So the value it will look like this. Load, the moment ILD of the moment due to unit load. Okay, so again this ordinate is nothing but 1.6. Okay, so if we solve this value MP, it is nothing but 20 into 1.6 plus half into 1.6 into 8 meter. Area which is coming under the UDL is 1.6 into it, and the intensity of the UDL which is 10 kilonewton per meter. Okay, so if what value I get from this is 20 into 1.6 plus 0.5 into 1.6 into 8 into 10. So the value comes out to be 96 kilonewton per meter. 96 kilonewton meter for this case. Okay, when this point load is acting just at the left of P. Remember that thing. Okay. Now Now this is okay. Now you can, so the value comes out to be 96 kilonewton per meter for this load for kilonewton meter. Okay. Now, if you see clearly from this load system, if I move this load 20 kilonewton meter to this side, 20 kilonewton load to this side. Okay. If my load condition, so let us suppose this is our beam. Okay, and this is point P, and this is the UDL. Let us suppose it is this distance is x, so this is 8 minus of x. Okay, and this load here, the some load is acting 10 kilonewton. Okay, this is so, and this distance is 2 meter and this is 8 meter. Okay, so if this is the load condition, and this is the 20 kilonewton load, this is acting at the right of the P. For this load condition, you can say that the max average load is nothing but 10 into x, 20 plus 10 into x equals to 20 plus 10 into x, 10 plus x upon my 8 should be equals to 10 kilonewton. Should be equals to 10 divided by 2. Okay, average load on this is on AP and this is on PB, right? So if we solve this problem, solve this equation, it will look like this. So 10x equals to minus, so x is coming out here negative, so there is no condition possible. So there is not a condition possible where this load should transfer to, should act at right of P. So okay, should act at right of P so that this value comes out to be maximum. Okay, so what we need to do over here is that we need to transfer x is coming out negative, means this value cannot hold. When this load is transferred, then 20 kilonewton load is transferred just at the right of P. Okay, because you can say that this 20 kilonewton, this is not, then the value is coming out to be negative. So this case is not possible. That for if we want to make average load on both the spans equal. Okay, so now what I will do over here, I will transfer this 20 kilonewton load to the left side of the beam, left side of the point P. Okay, if this is the point P, and I am transferring 20 kilonewton load at this point. Okay, so the distance between the load is 2 meters, so 10 kilometer will be automatically outside the beam. Okay, and this whole portion will covered by the UDL. Now I can write the average load on AP will be 20 plus 10x divided by 2, right? And let us suppose this is x. Okay, and equals to then this load on this system is nothing but 10 kilonewton meter, right? So this is the case. Okay, so 20 kilonewton. From here also it is, we are saying that x is coming 0, so 20 kilonewton should load should act at point P only. Okay, so this is the case which we are already getting, so we need not to consider this case. Okay, so now let us do one thing. Transfer this whole the whole beam is covered by the UDL. Okay, for this case you can see that the average load on AP equals to average load on PB. Okay, when x is coming out to be 0, means the P load is acting at this point only, and we have already discussed previously that concept. Okay, so now when the whole UDL is covered by the whole UDL is covered this length of the beam, then the average load automatically equals to this thing. Okay, so if I calculate the MP value for this case, we have already calculated, the value comes out to be 80 kilonewton meter, right? So in this case also, we are getting the maximum value 96 kilometer for the previous load which we have discussed, which this load combination. Okay, so this is the way you approach the problem, right? So if you have any doubt, you can write in the comment section. Okay, so guys, thank you very much.